The universe operates on a set of unbreakable laws. That is what we are taught. But what if the cosmos itself is the greatest rule breaker of all? We are about to journey through 30 astonishing moments where space defies scientific laws, where the very fabric of reality seems to contradict our deepest understanding. By the end, you will see the cosmos not as a predictable machine, but as a place of profound and thrilling mystery. We will encounter spacecraft that mysteriously slow down, a star that dims in impossible ways, and a force that pushes the universe apart. What cosmic secret do you find most compelling? Our first mystery began not with a bang, but with a whisper, a tiny, persistent drift in the data. As the Pioneer 10 and Pioneer 11 spacecraft sailed beyond the orbit of Pluto, scientists tracking their precise trajectories noticed something deeply unsettling. The probes were slowing down just a fraction more than they should have been. This was not a sudden stop, but an anomalous acceleration toward the sun, a minuscule force equivalent to a 10 billionth of the gravity you feel on Earth. Yet, over billions of miles, this whisper added up to thousands of miles of deviation. For decades, this pioneer anomaly stood as a glaring hint that our models of gravity, or perhaps of the universe itself, were incomplete. Could it be evidence of dark matter tugging at the spacecraft, or a flaw in Einstein's theory of general relativity on cosmic scales? The mystery captivated physicists, suggesting we might be on the brink of discovering entirely new laws. The answer, when it finally came, was a masterclass in scientific humility. Meticulous computer modeling revealed that the spacecraft themselves were the culprit. The faint but constant heat radiating from their nuclear power sources and electronics was pushing back on them, like a gentle but relentless breeze from a warm light bulb. This thermal recoil provided the exact amount of force needed to explain the anomaly. So, while the Pioneer anomaly did not rewrite the laws of physics, it perfectly illustrates how the cosmos challenges us. It presented a ghost in the machine, a signal that something was wrong, and it took decades of painstaking work to chase that ghost down to its source. This process, this confrontation with the unexpected, is how science truly advances, one meticulous investigation at a time. Just as one ghost was laid to rest, another, even more persistent specter appeared. This one haunted not the lonely depths of interstellar space, but the very doorstep of our own planet. It is called the flyby anomaly. For decades, mission controllers have used a clever trick to save fuel slingshotting spacecraft like Galileo and near Shoemaker around Earth to gain a gravitational boost, flinging them toward distant targets. The physics of these gravity assists are considered textbook, calculated down to the millimeter per second. Yet, repeatedly, these spacecraft have emerged from Earth's shadow with a tiny, unexpected kick. They gained or lost speed by a few millimeters per second, a difference so small it seems trivial, but in the precise world of orbital mechanics, it is a glaring error in the cosmic ledger. Imagine throwing a ball against a wall, predicting exactly how it will bounce back, only to watch it return to your hand with just a whisper more energy than it should have. That is the flyby anomaly. The numbers simply did not add up. Newton's laws and Einstein's refinements, which govern everything from falling apples to orbiting galaxies, predicted one velocity. The deep space tracking networks, listening to the spacecraft's radio signals, measured another. The discrepancy sent theorists scrambling. Could streams of dark matter be washing over Earth, subtly tugging on the probes? Was our model of Earth's gravity field, its lumpy and uneven distribution of mass, still not quite perfect? Or were there subtle, unaccounted for effects from Earth's rotation or its atmospheric drag at very high altitudes? Over the years, as our measurements of Earth's fluid became exquisitely detailed and our computer models more powerful, the anomaly for most flybys shrank, explained away by these finer details. But for a handful of spacecraft, a tiny, stubborn residual difference remains. It is a whisper that refuses to be silenced. To most scientists, it is likely the final echo of a measurement quirk, a testament to the incredible difficulty of modeling every single variable in a complex planetary encounter. But for others, that lingering whisper is a siren call. It is a reminder that sometimes the universe leaves a door ever so slightly ajar, hinting that our map of reality, while stunningly accurate, may still have unexplored corners waiting to be found. That stubborn whisper from Earth's flybys challenges our local physics, but a far louder cosmic alarm bell rings from the very edge of observable reality. It comes from the oldest light in the universe, the cosmic microwave background radiation. This faint, cold glow is the afterglow of the Big Bang itself, a snapshot of the infant cosmos when it was just 380,000 years old. For decades, this cosmic baby picture has been our strongest evidence for the standard model of cosmology. It shows a universe that is remarkably uniform, with tiny temperature fluctuations that seeded all the galaxies and voids we see today. And one of the most sacred principles drawn from this map is isotropy. The universe, on the largest scales, should have no preferred direction. It should look the same in all directions, a fundamental assumption of our cosmic worldview. But then, scientists looked closer. When they analyzed the detailed temperature patterns in this primordial light, they found something that should not exist. The fluctuations appear to align along a particular axis in the sky, a mysterious preferred direction that cosmologists, with a dark sense of humor, dubbed the axis of evil. This was not a small statistical fluke. The alignment suggested that one half of the universe might be subtly different from the other, that the cosmos has a kind of spine, a cosmic equator of significance. The implications are staggering. If true, it means the universe is not isotropic. It has a handedness, a lopsidedness written into its very foundations. This challenges the Copernican principle itself, the idea that we do not occupy a special place. Suddenly, our entire cosmic neighborhood might be oriented along this strange axis. What could cause such a thing? Theorists have proposed wild possibilities. Could it be the imprint of something that existed before the Big Bang, a pre-existing structure that stretched and imprinted itself onto the newborn cosmos? Or does it point to a flaw in our understanding of cosmic inflation, the rapid expansion that supposedly smoothed everything out? Perhaps our standard model of the universe is incomplete, missing a vital ingredient that gives space itself a subtle texture. Despite years of analysis and newer satellite data, the axis of evil has not gone away. It lingers in the maps, a profound and unsettling puzzle. It is a reminder that our most basic assumptions about the cosmos, the very pillars upon which modern cosmology is built, might be showing the faintest of cracks. And if those pillars tremble, what else might we discover hiding in the ancient light? The axis of evil hints at a cosmos with a hidden structure, but another, even deeper defiance is woven into the fabric of every single galaxy we see. This mystery begins with a simple, predictable rule from Isaac Newton. Just as planets closer to the sun orbit faster than those farther out, stars orbiting the center of a galaxy should behave the same way. The vast majority of a galaxy's visible mass, its stars and glowing gas, is concentrated in its bright central core. Therefore, stars out in the sparse, dark galactic suburbs should be moving relatively slowly, held by a weaker gravitational pull. This is not a suggestion. It is a direct prediction of Newton's law of universal gravitation, a law proven on Earth, in our solar system, and beyond. Yet, when astronomers like Vera Rubin began measuring the speeds of stars in spiral galaxies in the 1970s, they found something that shattered this expectation. Stars far out on the galactic edges were not moving slowly at all. They were racing around at nearly the same high speed as stars close to the brilliant center. It was as if the entire galaxy was embedded in an invisible, massive sphere of something, a ghostly gravitational glue holding these speeding stars in place and preventing them from flying off into the void. The visible galaxy we see, with all its hundreds of billions of stars, was just the tip of a monstrous, unseen iceberg. The math was undeniable. To explain the observed rotation, there had to be about 5 times more matter in the galaxy than we could see. This missing mass was given a simple, haunting name, dark matter. Today, dark matter is a cornerstone of cosmology. We map its immense, web-like scaffolding across the universe. We see how its gravity bends light from distant galaxies, and our entire model of cosmic evolution depends on it. Yet, after decades of the most sensitive experiments ever built, hunts deep underground in abandoned mines and in space, we have not directly detected a single particle of it. We know it exists by the ghostly handprint it leaves on everything, but we have no idea what it actually is. It defies not just gravity's predictions, but our every attempt to catch it. This profound ignorance has led some physicists to propose a radically different solution. What if we are not missing matter, but misunderstanding gravity itself? Theories like modified Newtonian dynamics, or MIND, suggest that on the vast, low acceleration scales of galactic outskirts, gravity behaves differently. The force does not fade with distance quite as Newton or Einstein predicted. In this view, there is no mysterious dark particle, only a subtle tweak to one of the universe's most fundamental laws. The debate is fierce. Does the cosmos contain a shadowy, unknown form of matter that makes up most of reality? Or are the laws of physics themselves not quite as universal as we thought? Every spinning galaxy is a crime scene, and we are still trying to determine whether the culprit is an invisible suspect or a broken rule. If dark matter is the ghostly hand shaping galaxies, dark energy is the phantom breath blowing the cosmos apart. This story begins with a seemingly straightforward question. After the Big Bang, the universe has been expanding for billions of years. Gravity, the great cosmic glue, should be pulling everything back together, gradually slowing that expansion. In the late 1990s, 2 independent teams of astronomers set out to measure this cosmic deceleration by studying distant stellar explosions called Type 1a supernova. These supernova are cosmic standard candles, exploding with a known, predictable brightness. By measuring how dim they appear from Earth, scientists can calculate their distance. By analyzing the color of their light, stretched by the expansion of space, they can determine how fast the universe was expanding when the star blew up. The teams expected to see that more distant, older supernova showed signs of a universe expanding more quickly in the past, confirming that gravity was indeed putting on the brakes. What they found instead was a shock that reverberated through all of physics. The most distant supernovae were fainter than they should have been. This meant they were farther away than anyone predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious force was overpowering gravity itself, pushing galaxies apart at an ever-increasing rate. The discovery was so profound and so unexpected that it earned the lead researchers the Nobel Prize in Physics in 2011. This force was given a name that echoes our profound ignorance: dark energy. Today, we believe it constitutes roughly 68% of the entire energy budget of the cosmos. It is not matter. It is a property of empty space itself, a repulsive pressure that acts like anti-gravity. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies. If the dough expands normally, the raisins move apart. But with dark energy, it is as if the dough itself is becoming springier, actively pushing the raisins away from each other faster and faster as the loaf grows. But what is it? The leading candidate is Einstein's cosmological constant, a sort of innate energy woven into the vacuum of space. Yet when theorists calculate how strong this vacuum energy should be based on quantum physics, the number they get is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. Alternatively, dark energy could be a dynamic field that changes over time, a cosmic cousin to the field that drove inflation just after the Big Bang. We simply do not know. Its nature is the single greatest mystery in modern cosmology because it dictates the ultimate fate of everything. If dark energy remains constant, the universe will expand forever, galaxies will vanish over the cosmic horizon, and the cosmos will end in a cold, dark, and lonely silence. If it grows stronger, it could eventually tear apart galaxies, solar systems, planets, and even atoms themselves in a catastrophic big rip. This is not a distant abstraction. Dark energy is shaping our cosmic destiny right now, and we have no idea what it is. We have given a name to our ignorance, and that name controls the future of all existence. While dark energy dictates the fate of the cosmos, a different kind of defiance is etched into the universe's birth certificate. We can rewind the clock to the universe's first few minutes, a period of unimaginable heat and density called Big Bang nucleosynthesis. In this primordial forge, protons and neutrons fuse to form the first atomic nuclei, the raw ingredients for every star and planet to come. Our mathematical models of this brief, violent epoch are exquisitely precise. They predict, with stunning accuracy, how much of the lightest elements should have been cooked up. The observed abundance of helium-4 in ancient gas clouds matches the prediction perfectly. The amount of deuterium, a heavier form of hydrogen, also aligns with the theory. These successes are pillars of the Big Bang model, confirming we understand the physics of the infant universe. But there is a glaring, persistent exception. The models also predict a specific amount of lithium-7, the third lightest element, and here, the universe presents us with a bill that does not add up. The oldest stars in our galaxy, which formed from nearly pristine material, show only about 1/3 of the lithium that our equations say should be there. 3 times less. This is not a minor rounding error. It is a fundamental mismatch between our most trusted nuclear physics and the actual chemical record of creation. Think of it as a cosmic recipe that has been tested 1,000 times. You combine hydrogen and helium in the heat of the early universe, following the instructions precisely, and you should get a certain amount of lithium. Yet when we look at the oldest samples of the cosmic batter, that key ingredient is mysteriously missing. So where did it go? One possibility is that our understanding of those first few minutes is still incomplete. Perhaps exotic, unknown particles from the early universe decayed and interacted with the nuclear soup, subtly altering the fusion chains and destroying lithium as it formed. Another line of thought points not to the birth, but to the childhood of the cosmos. Maybe the first generations of stars processed this primordial lithium, burning it up in their cores and never fully dispersing it back into space, effectively hiding it from our view in the atmospheres of ancient stars. Yet each proposed solution creates new problems, upsetting the beautiful agreement we have with helium and deuterium. The lithium problem stands as a quiet but profound rebellion. It tells us that a chapter in the story of our origins, a chapter we thought was closed and fully understood, still contains a hidden paragraph. For all our confidence in the Big Bang, a basic ingredient of the universe remains unaccounted for, a silent reminder that even our most successful cosmic models might be missing a crucial piece of the puzzle. The lithium problem points to a missing ingredient in our cosmic recipe, but for decades, cosmologists faced an even more embarrassing shortfall. They could not find half of the universe's ordinary matter. All the stuff that makes up you, me, planets, and stars is known as baryonic matter, composed of protons and neutrons. Our best models of the Big Bang and cosmic evolution tell us exactly how much of this normal matter should exist in the universe today. We can tally up the visible stars, the glowing gas in galaxies, and even the cold, dark clouds drifting in between. But when we added it all up, we came up staggeringly short. Nearly half of all the protons and neutrons predicted to exist were simply missing. It was as if we had a precise inventory for a cosmic warehouse, but a full 50% of the stock was unaccounted for. This was not exotic dark matter or mysterious dark energy. This was the ordinary atoms the universe is supposed to be built from, and they had vanished without a trace. The question haunted astronomers: where could you possibly hide half of all normal matter in plain sight? The answer, it turns out, was in the hottest and most tenuous places imaginable. Scientists theorized that the missing baryons might be hiding in the cosmic web, the vast, filamentary scaffolding of dark matter that structures the universe. In the immense voids between galaxy clusters, they predicted there should be strands of extraordinarily hot gas, heated to millions of degrees by the gravitational tumult of the cosmos forming. This gas would be so diffuse and so hot it would not emit visible light, rendering it invisible to traditional telescopes. To find it, astronomers turned to natural cosmic flashlights, quasars. These are the intensely bright cores of distant galaxies, powered by supermassive black holes. As the light from a quasar travels billions of light years to reach us, it passes through the intervening cosmic web. The superheated gas in those filaments, while invisible itself, leaves a fingerprint. It absorbs very specific wavelengths of the quasar's ultraviolet light. By analyzing the complex absorption lines in the spectra of hundreds of quasars, astronomers finally found the signature they were looking for. They discovered the missing half of all ordinary matter, not in bright galaxies, but in these colossal, seething rivers of gas that flow through the dark intergalactic voids. This was a mystery solved by defying our expectations of where matter should be. We had been looking for cosmic stuff in all the obvious, bright places, but the universe had tucked a vast reservoir of its normal material into the darkest, most energetic corners of the cosmic architecture. The missing baryons were never truly gone. They were just hiding in plain sight, in a state so extreme we had to learn a new way to see. We have found the universe's missing atoms, but some particles arrive at Earth carrying a message of pure defiance. They are called ultra-high energy cosmic rays, and they are the most energetic things we have ever detected in nature. These are not rays of light, but actual atomic nuclei, protons, and heavier elements, hurtling through space at nearly the speed of light. Their energy is staggering, millions of times greater than anything our most powerful particle accelerators, like the Large Hadron Collider, can produce. One detected in 1991 was so powerful it earned the nickname the "Oh my God" particle. It was a single proton carrying the kinetic energy of a professionally thrown baseball, all compressed into a subatomic speck. The existence of such particles is not the mystery. The mystery is that they should not be able to reach us. Our universe is not empty. It is filled with the faint glow of the cosmic microwave background, that ancient afterglow from the Big Bang. For a proton traveling at such insane speeds, this cosmic background radiation is no longer a harmless whisper. It becomes a wall of high-energy gamma-ray photons. According to well-established physics, when an ultra-high-energy cosmic ray smashes into one of these photons, it should trigger a reaction that bleeds away its colossal energy over a relatively short cosmic distance. This limit is known as the JZK cutoff, named for the scientists who predicted it. Essentially, particles with energies above this cutoff should be destroyed before they can travel more than about 150 million light-years. They are cosmic marathon runners who should collapse after the first few miles. Yet, we keep detecting them. The "Oh my God" particle and others like it are here. This presents two equally unsettling possibilities. First, there must be something within our local cosmic neighborhood, within that 150 million light-year bubble, that is acting as an unimaginable particle accelerator. We are talking about natural engines far more powerful than supernova or even active galactic nuclei. Some theorists point to colossal magnetic fields around merging galaxy clusters, or perhaps rare, hyper-energetic processes near supermassive black holes. But we have not convincingly identified such a monster next door. The second possibility is even more profound. What if our understanding of physics at these extreme energies is simply wrong? What if particles at such velocities interact with the cosmic background in ways we have not yet imagined, allowing them to travel much farther than the JZK limit allows? Each detection is like a postcard from a realm of physics we cannot yet access, telling us that either the universe hides accelerators of terrifying power just out of sight, or the rulebook for the most energetic events in existence still has missing pages. These cosmic rays challenge physics at its most extreme, but our entire galactic neighborhood is caught in a far grander and more mysterious motion. Our Milky Way is not drifting aimlessly through the cosmic expansion. It is racing, along with our entire local group of galaxies, at a breathtaking speed of over 600 kilometers per second toward a specific point in the constellation Centaurus. We are not alone in this headlong rush. Thousands of other galaxies across a vast swath of the universe are all streaming in the same direction, like leaves caught in a colossal, invisible river. This motion defies a fundamental expectation. Hubble's law tells us the universe is expanding uniformly, with galaxies generally moving apart from each other as space itself stretches. Yet here we have a huge volume of the cosmos moving in concert toward a single spot, a phenomenon astronomers call the bulk flow. It is as if the smooth, outward flow of an inflating balloon has a powerful, localized current flowing against it. Something out there, something of unimaginable mass, is pulling us. This gravitational phantom is known as the Great Attractor. The problem is we cannot see it. Our view toward this region of space is completely obscured by the dusty, star-filled plain of our own Milky Way galaxy. It is like trying to see a distant mountain range through a thick, permanent fog bank. For decades, the Great Attractor was a profound shadow on our maps, a blank spot in the sky hiding a cosmic secret. To peer through the galactic smog, astronomers had to abandon visible light and turn to instruments that see in radio and X-ray wavelengths. These can penetrate the dust, revealing what optical telescopes cannot. What they found was not a single, monstrous object, but an overwhelming concentration of mass. The heart of the Great Attractor region is dominated by the Norma cluster, a dense gathering of thousands of galaxies, and the even more massive Laniakea supercluster, of which our Milky Way is just a distant suburb. The combined gravitational pull of these immense structures is immense, certainly enough to influence the motion of galaxies for hundreds of millions of light years around them. But here is the lingering puzzle. When scientists add up all the visible mass in these superclusters, the numbers still seem to fall short. The pull we feel appears to be stronger than what the visible galaxies, gas, and dust can account for. This suggests the Great Attractor might not be one thing, but a focal point where multiple rivers of dark matter converge, a dense knot in the cosmic web where both seen and unseen matter create a gravitational sink of staggering proportions. The hunt is not over. We are still mapping this hidden realm, discovering ever larger structures that contribute to the flow. The Great Attractor teaches us that we are not passive observers of an expanding universe. We are participants in a grand, dynamic tug of war, pulled by hidden giants whose full nature remains just out of sight. A constant reminder that even the motion of our galaxy is a clue to a deeper cosmic architecture. The Great Attractor pulls us through a hidden cosmic landscape, but woven through that very landscape is another invisible force, one that shapes the birth of stars and guides the paths of cosmic rays. It is the magnetic field of our galaxy. We often think of magnetism as a local phenomenon, the pull of a simple bar magnet, or the gentle tug of Earth's own protective field. Yet the Milky Way possesses a magnetic field of staggering scale, a coherent structure that spans over 100,000 light years from end to end. This is not a simple north-south bar magnet in space. It is a complex, twisting web of magnetic lines, with spiraling arms and turbulent bubbles, all aligned on a scale that defies easy explanation. How does a galaxy, a swirling disk of tenuous gas and 100 billion stars, generate and maintain such an immense, organized magnetic structure? The leading theory is called the galactic dynamo. Imagine a simple bicycle dynamo. You turn a wheel which spins a magnet inside a coil of wire, generating an electric current. A galaxy operates on a similar, but vastly more complicated, principle. The rotation of the galaxy provides the initial spin. The turbulent motions of ionized gas within the disk, churned by supernova explosions and stellar winds, act like the chaotic motion of the wire. This moving, conductive gas can, in theory, stretch and twist any weak, pre-existing magnetic field, amplifying it over hundreds of millions of years into the powerful fields we detect today. But here lies the catch, a classic cosmic chicken and egg problem. A dynamo cannot start from nothing. It requires a seed, a tiny initial magnetic field to amplify. Where did that first, faint galactic magnetic field come from? This is one of the most profound puzzles in astrophysics. We must look back to the universe's infancy, to a time before the first stars or galaxies even formed. In that primordial darkness, what process could have imprinted a magnetic whisper across the cosmos? The possibilities push at the edges of known physics. Some theories suggest these seed fields were generated in the extreme violence of the Big Bang itself, perhaps through phase transitions in the seething energy of the newborn universe, a process that would involve physics far beyond our standard model. Others propose they were created later by the very first generation of stars, whose powerful stellar winds and cataclysmic deaths could have magnetized their surroundings, seeding the intergalactic medium before galaxies fully assembled. There is even a fascinating idea that these fields were born in the vast emptiness between galaxies, sparked by shock waves from the first collapsing cosmic structures. The challenge is that these primordial magnetic fields, if they still exist, would be incredibly weak, billions of times fainter than Earth's magnetic field, and nearly impossible to detect directly. Yet their legacy is everywhere, in the ordered magnetism of every spiral galaxy we see. This means we are forced to deduce the existence of a ghost from the shape of its haunted house. The magnificent magnetic tapestry of our galaxy, which guides cosmic particles and sculpts gas clouds, may ultimately be the amplified echo of a whisper from the dawn of time, a whisper whose origin remains one of the universe's best-kept secrets. Galactic magnetism whispers of ancient origins, but our own star presents a paradox that strikes at the heart of life's story. Billions of years ago, when the first single-celled organisms were emerging on a young Earth, our sun was a weaker, dimmer star. According to our well-tested models of stellar evolution, the newborn sun should have been about 30% less luminous than it is today. That simple fact leads to a chilling prediction. Under that faint young sun, Earth's early climate should have been a global deep freeze. The entire planet should have been locked in ice, a glittering snowball incapable of supporting liquid water, let alone the delicate chemistry of life. Yet the geological record screams the opposite. We find ancient rocks, some nearly 4 billion years old, that show clear signs of being shaped by liquid water. We see evidence of sedimentary deposits and even the fossilized remains of early microbial life. The Earth was warm and wet, not frozen solid. This glaring contradiction is the faint young sun paradox, a direct clash between the laws of astrophysics and the hard evidence written in stone. It defies our most straightforward climate models, which tell us that a weaker sun means a colder planet. So how did Earth stay warm? The leading solution points to a planetary blanket, a greenhouse effect far more potent than today's. Our ancient atmosphere may have been rich with gases like methane or carbon dioxide at concentrations hundreds of times greater than present levels. These gases, efficient at trapping infrared heat, could have provided the extra warmth needed to offset the sun's faint glow. Another possibility involves Earth's own reflectivity, or albedo. With fewer continents and a different cloud cover, the young planet might have absorbed more sunlight rather than bouncing it back into space. Some even suggest subtle shifts in Earth's orbit or tilt played a role, but each solution carries its own mysteries. If greenhouse gases were so high, what process eventually drew them down? And why did the climate stabilize rather than spiral into a runaway heat trap? The paradox reminds us that planets are complex, interacting systems. It is not enough to know the star's output. You must understand the atmosphere, the oceans, the geology, and even the life itself, all dancing in a delicate thermal balance. This ancient enigma is more than a puzzle about our past. It is a guiding principle in our search for life beyond Earth. When we look at distant, faint stars and find planets in their habitable zones, we must ask, what is keeping them warm? The answer may require a planetary recipe far more intricate than we ever imagined. The faint young sun paradox shows how a planet can defy expectations, but some cosmic events defy explanation entirely. Across the universe, in galaxies billions of light years away, something is screaming. For just a millisecond, a point in space unleashes a blast of radio waves so powerful it outshines the collective energy output of our own sun for days, sometimes even months. Then, just as suddenly, it vanishes. These are fast radio bursts, or FRB. They are the universe's most intense and most baffling flashes, cosmic lightning strikes of unknown origin. Their extreme brevity is what makes them so maddening to study. They appear without warning from random points in the sky, a blip of interference that is over before our largest radio telescopes can fully swivel to look. For years after their discovery, each one was a singular, cataclysmic mystery. Was it the final death cry of a star being shredded by a black hole? Or perhaps the collision of two incredibly dense neutron stars? The rules seemed clear. Such unimaginable energy must come from an unimaginable, one-time destruction. Then everything changed. Astronomers found an FRB that did not play by those rules. It repeated. From the same patch of distant sky, another brilliant millisecond flash erupted, and then another. This single discovery shattered the leading model. Whatever was producing these bursts was not destroying itself. It was surviving. It was a repeating engine of cosmic violence. This pointed the finger squarely at one of the universe's most magnetic and volatile objects, the magnetar. Imagine a neutron star, the collapsed core of a giant star, crushed into a city-sized sphere of pure, screamingly dense matter. Now, wrap it in a magnetic field 1,000 trillion times stronger than Earth's. That is a magnetar. These objects are known for starquakes and colossal magnetic eruptions, events theoretically capable of generating the raw power of an FRB. The repeating bursts fit the idea of a persistent, hypermagnetic object having periodic fits of fury. But the story is far from solved. The precise engine and the exact emission mechanism remain utterly elusive. How does a magnetar, or any object, concentrate the energy of a star's lifetime into a radio flash that lasts less than the blink of an eye? The physics involved is at the very edge, and perhaps beyond, our understanding of matter and magnetism in the most extreme environments. Some bursts even show bizarre, intricate patterns in their polarization, as if the radio waves have been twisted by traversing incredibly powerful magnetic fields, adding another layer of mystery. Fast radio bursts are more than just distant curiosities. They are probes. As their fleeting signals travel across the cosmos, they pass through the diffuse gas between galaxies. This subtly slows different radio frequencies, leaving a fingerprint of all the material they have traversed. In this way, FRBs are helping us map the universe's missing ordinary matter, the very baryons we once could not find. So these enigmatic flashes are both a profound defiance and a potential tool. They represent a fundamental gap in our knowledge of how the universe operates at its most violent extremes, while simultaneously offering a new way to see the invisible scaffolding of all existence. We are left listening to the static, waiting for the next millisecond scream to teach us something new. That millisecond scream of an FRB is a modern mystery, but the search for cosmic signals has one legendary, lonely artifact. On a quiet August night in 1977, at the Big Ear Radio Telescope in Ohio, a narrowband signal burst through the cosmic static for 72 glorious seconds. It was so powerful, so perfectly aligned with the expected signature of an artificial transmission, that the astronomer reviewing the data printout, Jerry Amon, circled the alphanumeric sequence and wrote a single, awestruck word in the margin, "Wow." This was not random noise. It was a sharp, intense spike at exactly 1420 megahertz, a frequency that is naturally silent, protected by international agreement because it is where hydrogen, the most common element in the universe, quietly whispers. For that brief window, something or someone appeared to be shouting on a cosmic channel reserved for listening. The signal rose and fell exactly as a fixed telescope would see a point source drift through its field of view, a perfect match for a transmission from a fixed location in space. It bore all the hallmarks of a beacon, and then it vanished. Despite decades of targeted searches by projects like SETI, listening intently to that same patch of sky in the constellation Sagittarius, the WOW signal has never repeated. Not a whisper, not an echo. Its solitary nature is what makes it so profoundly defiant. Natural cosmic events like pulsars or stellar flares repeat. They are governed by physics that cycles and pulses. But a one-off event of such precise, artificial-looking characteristics that challenges our entire framework for what is possible. Astronomers have scrambled for explanations. One recent suggestion pointed to a passing comet, releasing a cloud of hydrogen that could theoretically emit at that frequency. But the comets proposed were not in the right part of the sky at that precise time, and the mechanism is considered far too weak to produce such a powerful, clean signal. Other ideas, like a chance amplification from a distant star's gravitational lens or some unknown, fleeting astrophysical transient, feel like strained attempts to fit a square peg into a round hole. The signal simply does not match any known natural phenomenon we have cataloged before or since. It stands alone, a 72-second enigma etched into a roll of computer paper. In a universe filled with the chaotic roar of natural processes, the WOW signal was a perfect, coherent tone. It is the ultimate cosmic tease, a single page torn from a book we will never read, leaving us to wonder if, for one moment in 1977, we accidentally overheard a conversation not meant for us. The WOW signal was a fleeting whisper, but another star holds a secret that refuses to fade. In the constellation Cygnus, over 1,000 light-years away, a seemingly ordinary star named Tabby 84628552, now better known as Tabby's star, began behaving in a way that defied every astronomical textbook. The Kepler Space Telescope, designed to hunt for planets by spotting the regular, gentle dips in starlight as they transit, found something utterly different here. This star did not dim in a predictable, repeating rhythm. Instead, it plunged into darkness erratically, with some dips blocking an astonishing 22% of its light. A planet, even a gas giant, would only cause a drop of about 1%. This was something else, something colossal and bizarrely structured, passing between us and the star. The dimming patterns were jagged, asymmetric, and deeply irregular. Sometimes the star would fade slowly and brighten quickly. Other times it would flicker with multiple, smaller dips nested inside a larger one. It looked less like an orbiting object and more like a swarm of something, a cosmic cloud of unknown shapes drifting through our line of sight. The scientific community scrambled for explanations, each one pushing the limits of known physics. The leading natural hypothesis invoked a giant swarm of comets, perhaps thousands of them, shattered by a close encounter with the star and now trailing in a vast, dusty debris field. But to cause dips that deep, the swarm would have to be unimaginably dense, a collection of fragments on a scale we have never seen around any other star. Other ideas pointed to the aftermath of a planetary collision, a cloud of pulverized rock and ice, or even an immense, intervening cloud of interstellar dust that just happened to be drifting past. Yet each natural model struggled to explain the precise, chaotic patterns of the dimming without requiring a series of unlikely cosmic coincidences. This persistent strangeness opened the door to a more speculative, thrilling possibility. Could we be witnessing the construction of an alien megastructure? The idea, popularized as a Dyson swarm, suggests a civilization advanced enough to build a vast array of energy-collecting satellites or habitats orbiting its star, capturing its total output. Such a structure would be irregular, block light in strange ways, and could account for the huge, non-repeating dips. While astronomers consider this the least likely explanation, its very plausibility highlights how deeply Tabby's star defies classification. It is not just an oddity, it is a challenge. It forces us to confront the limits of our categories, showing us that stellar behavior exists on a spectrum far wider and weirder than we ever assumed. In the quiet dimming of a distant sun, we find a reminder that the universe is still perfectly capable of writing mysteries for which we have no ready answer. Tabby's star is a mystery of missing light, but Saturn presents a ghost of perfect geometry. At its north pole, hidden for decades in the long shadow of its winter, the Cassini spacecraft revealed a sight that stunned planetary scientists. There, etched into the planet's swirling cloud tops, is a perfect, persistent hexagon. This is not a fleeting cloud formation or a trick of the light. It is a six-sided jet stream, a colossal hurricane of gas with walls of cloud over 100 miles high, spinning around a central vortex. The scale is almost impossible to grasp. Each side of the hexagon is wider than the diameter of Earth. This single, stable weather pattern could swallow our entire planet with room to spare. And it has likely been there for decades, perhaps even centuries, a permanent fixture in Saturn's turbulent, gaseous sky. This is where the defiance begins. In fluid dynamics, the study of how liquids and gases flow, nature strongly prefers circles and spirals. Think of hurricanes on Earth, the great red spot on Jupiter, or water swirling down a drain. These are vortices, and their natural shape under rotation is circular or elliptical. A stable, geometric shape with sharp, 60-degree corners is a profound anomaly. It is as if you stirred a cup of coffee and watched a perfect triangle or square form in the cream. On a planet where winds scream at over 300 miles per hour and storms rage for lifetimes, how can this pristine hexagon hold its shape against the chaos? The answer lies in an elegant dance between rotation and shear. Laboratory experiments here on Earth have shown a path to this strange geometry. When a fluid like water is placed in a circular container and the center is rotated at a different speed than the outer edge, waves can form in the fluid's boundary layer. Under very specific conditions of speed and viscosity, these waves can organize into stable polygons, squares, triangles, and yes, hexagons. The key is a steep gradient in wind speed, a sharp boundary where one band of atmosphere is moving much faster than its neighbor. Saturn's atmosphere is a layered onion of such jet streams. Scientists believe the hexagon marks the boundary of a particularly intense, eastward flowing jet at the planet's north pole. The deep, churning atmosphere below may be acting like that rotating container in the lab, setting up a standing wave pattern that pins the jet stream into this six-sided shape. But the laboratory analogy only goes so far. Our tanks are centimeters across. Saturn's hexagon is tens of thousands of kilometers wide. Our experiments last for minutes. Saturn's has endured for generations. The sheer scale and stability of this atmospheric artifact push our fluid dynamics models to their absolute limit. We still do not fully understand how the pattern is so sharply confined. or what gives it such remarkable longevity in a system of unimaginable violence. The Saturn hexagon is a breathtaking demonstration that the universe has a hidden fondness for order, crafting perfect angles from the formless fury of a gas giant's heart. It is a cosmic signpost, reminding us that even in the realms of pure chaos, there can be rules we are only beginning to decipher. Saturn's hexagon is a masterpiece of fluid dynamics, but our solar system holds a ghost of a different kind, a phantom structure defined entirely by what we cannot see. Far beyond the orbit of Neptune, beyond even the scattered disk of icy objects, lies the theoretical boundary of our sun's gravitational influence. This is the realm of the Oort cloud, a vast, spherical shell of frozen relics from the solar system's birth. Imagine a collection of perhaps trillions of icy planetesimals, each a dormant comet nucleus, orbiting in the deep freeze of interstellar space. This is the source of the long-period comets, those spectacular, unpredictable visitors that plunge into the inner solar system from random directions, their orbits suggesting a distant, spherical reservoir rather than a flat belt. We accept its existence as a fundamental part of our cosmic story, and yet, not a single object within the Oort cloud has ever been directly observed. It is a frontier mapped only by the trails of its messengers. The paradox is profound. This cloud is thought to begin roughly 2 times farther from the Sun than Earth, and extend outward for perhaps a light year, nearly a quarter of the way to the next star. At such distances, the Sun is just a particularly bright star in a dark sky. The objects there, if they reflect any sunlight at all, are far too faint for our most powerful telescopes to pick out against the blackness. So we are left inferring an entire domain from the comets that occasionally fall inward. It is like deducting the shape and size of a distant forest by studying only the rare leaves that blow into your town on a storm wind. The very evidence for the Oort cloud is its defiance of direct detection, a structure that must exist to explain what we see, yet remains forever just beyond our sight. This leads to an even deeper mystery of origins. How did this cloud form so impossibly far from the Sun? The prevailing theory is a story of gravitational pinball in the solar system's violent youth. As the giant planets like Jupiter and Saturn coalesced, their immense gravity hurled a fraction of the early system's icy building blocks outward in a grand cosmic slingshot. Some were ejected entirely, becoming rogue nomads between the stars. Others were sent on such vast, elongated orbits that they only loosely feel the Sun's tug, settling into that distant spherical halo. But the process is not static. The Oort cloud is not a serene, frozen archive. It is constantly being sculpted by external forces. The gentle but relentless pull of the Milky Way's gravity, the tidal force of the galactic disk itself, can stir these distant orbits, occasionally prying a comet loose to begin its long fall sunward. Even more dramatic are the rare close passages of other stars, which can plow through this distant cloud like a ship through fog, disrupting countless orbits and sending a shower of comets inward over millions of years. So the Oort cloud represents the ultimate frontier of our solar system, a place where our knowledge is built on brilliant deduction rather than direct light. It is a ghostly presence, its structure and population shaped by the gentle tides of the galaxy and the chance encounters of passing suns. Every long-period comet that graces our night sky is a refugee from this unseen realm, a fleeting glimpse into the dark, frozen edges of our own celestial home, reminding us that the boundaries of our knowledge are still drawn in the faintest lines of inference. The Oort cloud marks the theoretical edge of our sun's influence, but closer in, A different gravitational ghost may be pulling the strings. Astronomers studying the frozen debris beyond Neptune have stumbled upon a pattern that should not exist. A handful of extreme trans-Neptunian objects, small icy worlds with orbits taking thousands of years, share a peculiar trait. Their elongated paths are mysteriously clustered, as if something massive is herding them, shepherding their orbits to align in a specific orientation in space. According to the laws of orbital mechanics, these distant orbits should be randomly oriented, scattered like needles dropped on a floor. Their distinct alignment points to an unseen shepherd, a gravitational fingerprint hinting at a hidden giant. This is the core of the Planet 9 hypothesis, the tantalizing idea that a world larger than Earth, perhaps up to 10 times its mass, lurks in the perpetual twilight of the outer solar system, completing a single orbit once every 10 to 20 years. This would not be a simple addition to our planetary family. It would be a revolutionary defiance of our solar system census, a colossal world that somehow evaded detection during the formation of the other planets, or was captured from another star entirely. Its existence would rewrite the story of our own cosmic backyard. The hunt for this phantom world is a modern astronomical detective story of the highest order. Scientists are not scanning the skies randomly. They are using the clustered orbits of those distant objects as a celestial treasure map, calculating where in its immensely long, slow orbit this hypothetical planet must be to create the observed gravitational patterns. The challenge is staggering. At its predicted distance, hundreds of times farther from the Sun than Earth, Planet 9 would be incredibly dim, reflecting only the faintest whisper of sunlight. Spotting it is like searching for a single lump of charcoal in the vast darkness of a cavern, using only the flicker of a distant match. The most powerful telescopes on Earth and in space are engaged in this meticulous, pixel-by-pixel search, hoping to catch the slow drift of a single point of light against the fixed backdrop of stars. Yet, as with any good mystery, alternative explanations exist. Could the orbital clustering be an illusion, a trick of observational bias, because we have only found a few of these extreme objects? Perhaps the collective gravity of many smaller, unseen icy bodies in the distant disk could produce a similar shepherding effect over billions of years, eliminating the need for a single large planet. The debate is fierce and ongoing. Each new discovery of a distant object either tightens the case for Planet 9's gravitational hand or loosens it. This search epitomizes science at its most thrilling, a pursuit driven by a pattern in the data that whispers of a hidden rule breaker, a world waiting in the dark to either confirm our predictive power or reveal an entirely new chapter in the dynamic history of our solar system's furthest reaches. These hidden giants could reshape our solar system, but on a far smaller scale, a different kind of cosmic limit is being tested. A neutron star is the collapsed heart of a massive star, a city-sized object with the mass of our sun squeezed into a sphere just a dozen miles across. A single teaspoon of its material would weigh billions of tons on Earth. Under such unimaginable pressure, the star's outer layers are crushed into a crystalline crust of pure neutrons, a substance harder than any diamond and 10 billion times stronger than steel. This crust is thought to be phenomenally smooth, bound by gravity so intense it should flatten any surface irregularity to near perfection. For decades, physicists calculated that the tallest possible mountain on a neutron star, a tiny bump on this impossibly dense surface, could be no more than a few millimeters high. That is the theoretical limit, the point where the crust's own immense strength would shatter under the star's gravitational pull. But the universe loves to test limits. Recent studies of gravitational waves, the ripples in spacetime caused by cataclysmic events, have hinted at something extraordinary. Some neutron stars might not be perfectly smooth. They could possess mountains not of rock, but of ultra-dense nuclear matter, reaching perhaps a centimeter in height. To our eyes, that is nothing. On the scale of a neutron star, it is a colossal, jagged Himalaya. A feature that size would represent a titanic deformity, a monument to the crust's ability to withstand forces that should, by all rights, crush it into uniformity. The implications ripple through physics. A centimeter-high mountain would not be a gentle hill. It would be a massive asymmetry, a lump of concentrated mass whirling around hundreds of times per second as the star spins. This creates a wobble, a continuous disturbance in the star's gravitational field that would broadcast powerful, detectable gravitational waves across the cosmos. Finding such a signal would be a direct observation of these impossible mountains. But their existence would force us to rewrite the recipe for neutron star crusts. Deep within, physicists believe the matter undergoes bizarre phase transitions, forming structures known as nuclear pasta. Under increasing pressure, the neutrons arrange themselves into shapes resembling spaghetti, lasagna, and gnocchi, a bizarre landscape where nuclear forces and gravity battle for dominance. A crust capable of supporting centimeter-high mountains suggests this nuclear pasta layer is far stranger and stronger than our models predict. It might have a tensile strength beyond anything we've calculated, or contain exotic, unknown states of matter that reinforce it like cosmic rebar. This defiance is not about size, but about the fundamental nature of matter itself. A bump the height of a fingernail on a star 20 kilometers wide could be the key to unlocking the secrets of physics at its most extreme. The battle between a neutron star's crust and its own gravity is a clash of titans, but a deeper conflict unfolds at the edge of a black hole, a paradox that threatens to unravel reality itself. It begins with Stephen Hawking's most shocking discovery. Black holes, we once thought, were the universe's ultimate endpoints. Nothing, not even light, could escape their gravitational grip. But Hawking applied quantum theory to the curved space just outside a black hole's event horizon. He realized that the intense gravitational field could spontaneously create pairs of particles and antiparticles from the vacuum of space itself. Normally, such a pair would instantly annihilate, but at the horizon, a freak event can occur. One particle falls into the black hole, while its partner escapes into space, carrying away a tiny amount of energy. To an outside observer, this stream of escaping particles looks like a faint thermal glow, now called Hawking radiation. This radiation is purely thermal, meaning it is random noise, like the static from an untuned radio. It contains no specific information about what fell into the black hole, whether it was a star, a spaceship, or a library of books. It is just heat, and here lies the heart of the paradox. As the black hole emits this radiation, it loses mass, slowly evaporating. Over trillions of years, a black hole could theoretically shrink away to nothing, vanishing completely. If that happens, everything that ever crossed its event horizon, every atom, every bit of data that made up those objects, would be gone forever. The Hawking radiation left behind would be a featureless puff of thermal noise. This violates one of the most sacred principles in quantum mechanics, a law called unitarity. In the quantum world, information is never truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. Think of burning a book. The ashes and smoke seem like a loss, But if you could track every molecule and reconstruct every chemical reaction, you could, in theory, rebuild the book. Unitarity says the universe always keeps a perfect ledger. Hawking's calculations suggested black holes are cosmic shredders, burning the ledger itself. This is the black hole information paradox, a direct war between Einstein's theory of gravity, which says things fall into black holes and are gone, and quantum mechanics, which says information must be preserved. How can both be true? Proposed solutions are as mind-bending as the paradox. One leading idea comes from the holographic principle. It suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across its surface. As the black hole evaporates, this information is slowly and chaotically leaked back out in the Hawking radiation, scrambled beyond recognition but technically preserved. Another, more violent proposal is the firewall hypothesis. It argues that to prevent information loss, the event horizon cannot be the smooth gateway general relativity predicts. Instead, it must be a wall of searing energy, a literal firewall that incinerates anything crossing it, preserving information by converting it into a blast of radiation immediately. Both ideas defy our classical intuition, pointing toward a reality where space itself has a fundamental graininess, and where the smooth fabric of spacetime breaks down under extreme conditions. This paradox is not just an academic puzzle. It is a glaring signal that our two most successful theories of reality, general relativity and quantum mechanics, are fundamentally incompatible at this edge. Solving it may require a revolution in physics, a new set of laws where information, spacetime, and gravity are woven together in a way we have not yet begun to imagine. While black holes challenge our grasp of information, a different crisis is unfolding on the grandest scale of all, measuring the very speed of the universe's expansion. This speed is quantified by a single, crucial number, the Hubble constant. It tells us how fast galaxies are moving away from us for every megaparsec of distance, essentially the current expansion rate of the cosmos. Pinpointing this number should be one of the crowning achievements of modern cosmology, a fundamental parameter to describe our universe. Instead, it has become a source of profound and growing discord. Two of our most trusted methods for measuring this constant are now giving us stubbornly different answers, a discrepancy so significant it has earned a dire name, the Hubble tension. One method looks back to the universe's infancy. By studying the detailed patterns in the cosmic microwave background, that snapshot of the newborn cosmos, we can extrapolate forward using our standard model of cosmology, called lambda CDM. This model includes dark energy and cold dark matter. It tells us how the expansion should have evolved from the first moments to today. This early universe measurement gives us a very precise value for the Hubble constant. The other method measures the universe's current local expansion directly. We use cosmic lighthouses, like Type 1, a supernova, and pulsating stars called Cepheids, to gauge distances to nearby galaxies. By comparing their distances to how fast they are receding, we get a direct read on the Hubble constant right now. These are not rough estimates. Both methods are exquisitely precise, the result of decades of work with space telescopes and massive sky surveys. And that is what makes the results so shocking. They do not agree. The local late universe measurement says the cosmos is expanding noticeably faster than the early universe measurement, when run through our standard model, says it should be. The gap is not large in everyday terms, but in the world of precision cosmology, it is a chasm. The chance that this is a simple statistical fluke is now vanishingly small, less than 1 in a million. This is not an error bar, it is a crisis. The persistence of the Hubble tension suggests a potential flaw in our standard cosmological model itself. Lambda CDM has been spectacularly successful, but this tension is a crack in its foundation. Scientists are now forced to ask, what ingredient are we missing? One compelling idea is early dark energy. This proposes that a transient form of dark energy, a sort of cosmic booster rocket, existed for a brief period in the very early universe, altering the expansion history just enough to make the early and late measurements misalign today. Another possibility lies in the properties of neutrinos, those ghostly particles that barely interact with matter. What if they are not quite as light or as simple as we think? Exotic neutrino properties could subtly change how structures formed, impacting our calculations. There are even suggestions that dark matter might not be completely cold, but have a slight warmth to it, giving it a small amount of early motion that changes the cosmic recipe. Each proposed fix is radical, requiring new physics beyond our current understanding. The Hubble tension is more than a number puzzle. It is a direct challenge from the cosmos. It tells us that our map of universal history, from the first flash of the Big Bang to the galaxies we see today, might have a crucial page missing. As measurements get even more precise, the tension only tightens, forcing cosmologists to a thrilling and uncomfortable frontier, where the only way forward may be to rewrite the rules of the universe's expansion. This precise clash between prediction and observation is the heart of the GZK paradox. The Greisen-Zatsepin-Kuzmin cutoff is not just a suggestion. It is a firm theoretical wall built from well-understood physics. When a proton with unimaginable energy, above about 8 times 10 to the 19th electron volts, races across the universe, it is not traveling through empty space. It is plowing through the cosmic microwave background, that sea of ancient photons. Each collision between this ultra-high energy proton and a low-energy photon is like a cosmic car crash. It produces new particles, sapping the proton's energy in a process called photopian production. Over a distance of roughly 150 million light-years, this process should drain these cosmic bullets of their extraordinary punch, bringing them below the cutoff energy. No proton from a distant galaxy should reach Earth with energy above that limit. It is a clear, testable prediction. The universe, however, seems to enjoy threading the needle. The vast majority of ultra-high energy cosmic rays detected by massive observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah do, in fact, have energies just below the GZK cutoff. This is a triumph for the theory, confirming that the process is real and that these particles are being attenuated over long distances. But then there are the outliers. Every few years, detectors catch a particle that appears to have an energy above the wall. The most famous, the "Oh my God" particle, was one such event. These detections ignite the debate. Do these rare events represent a true paradox, a defiance of the GZK limit, or are they simply the statistical flukes at the very edge of our measurement capabilities? The detective work is immense. The Pierre Auger Observatory, for instance, is not a single telescope. It is an array of over 1,600 water tanks spread across an area the size of Rhode Island, alongside telescopes that watch for faint ultraviolet flashes in the sky. When an ultra-high energy cosmic ray strikes Earth's atmosphere, it creates a cascade of secondary particles, an air shower. The Auger tanks detect these particles when they reach the ground, while the telescopes capture the faint glow of the shower developing. By combining these signals, scientists can reconstruct the energy and direction of the original cosmic ray with remarkable precision. The ongoing analysis is a meticulous process of calibration and cross-checking, ruling out instrumental errors or rare atmospheric phenomena. The current consensus leans toward the universe obeying its own rules. As data accumulates, the evidence for a true GZK suppression grows stronger. Many of the events that initially seemed above the limit have been revised downward with better analysis and understanding of the detectors. Yet, the possibility of a genuine anomaly has not been completely extinguished. It pushes scientists to consider exotic explanations. Could these super-energetic particles be much heavier atomic nuclei like iron, which interact with the background radiation differently than protons? Or do they come from surprisingly nearby sources, within that 150 million light-year safe zone, where our maps of potential cosmic accelerators are still incomplete? This cosmic detective story epitomizes how the universe tests the limits of our knowledge. It presents a stark prediction, allows us to build colossal experiments to test it, and then delivers answers that are both confirmatory and tantalizingly ambiguous. The GZK paradox may ultimately be resolved in favor of established physics, but the pursuit of that resolution forces us to sharpen our tools and question our assumptions, ensuring that even the walls we build in theory are constantly probed by the relentless curiosity of observation. That cosmic particle wall is a testament to the universe's invisible barriers, but another barrier of a different kind appears etched into the first light of creation itself. In the detailed maps of the cosmic microwave background, that baby picture of the universe, there exists a feature so bizarre it has earned a chillingly simple name: the cold spot. This is not a minor temperature fluctuation. It is a vast, circular region in the constellation Eridanus that is significantly colder than the surrounding sky, a cosmic bruise on the face of the newborn universe. Its size and its profound chill make it a profound statistical outlier. According to our standard model of cosmic inflation, which predicts a generally uniform distribution of these tiny temperature variations, the odds of such an extreme cold patch appearing by random chance are less than 1 in 200. It is an anomaly that refuses to be smoothed away by better data. So what could possibly leave a frozen fingerprint on the universe's birth certificate? Theorists have proposed explanations that sound like science fiction. One of the most breathtaking ideas suggests the cold spot is a cosmic scar, the imprint of a collision with another universe. In the multiverse scenario, our universe is one bubble in a frothing sea of other bubble universes, each with its own physics. If, during inflation, our expanding bubble universe grazed another, the energy of that collision could have drained away from a region of our sky, leaving it noticeably colder in the afterglow. It is a staggering concept, the first potential empirical evidence for a reality beyond our own. A more conventional, yet still exotic, explanation lies within our own universe. Perhaps the cold spot is not a feature of the CMB itself, but a shadow cast by something immense between us and that ancient light. This is the supervoid hypothesis. Imagine a truly colossal region of space, billions of light years across, that is unnervingly empty, a desert with far fewer galaxies and clusters than the cosmic average. If such a void existed along our line of sight to the cold spot, the journey of CMB photons through it would be affected by a subtle but powerful effect. As photons enter the underdense region, they expend energy climbing out of the void's weaker gravitational well. In an expanding universe, This loss of energy is not fully recovered, causing the photons to redshift slightly, making them appear colder to us. This integrated Sachs-Wolf effect could, in theory, imprint a cold patch on the CMB map. The hunt for this phantom void became a cosmological priority. Astronomers scanned the region, counting galaxies and measuring their distribution. Initial surveys did find evidence of a large underdense region, but its size and emptiness did not seem sufficient to explain the profound coldness of the spot. The void, while real, appeared too shallow to cast such a deep shadow. Later, more comprehensive surveys using galaxies as tracers for mass presented an even murkier picture. Some found no significant supervoid at all in the precise direction of the cold spot, while others suggested a complex of smaller, connected voids that might combine to produce the effect. The evidence is contradictory and fiercely debated. This leaves cosmology at an impasse. The most tantalizing exotic explanation, the multiverse collision, remains untestable with current technology. The leading internal explanation, the supervoid, lacks the conclusive evidence needed to close the case. The cold spot therefore endures, a ghostly smudge on our most sacred map. It is a quiet, persistent reminder that our universe's first light might still hold echoes of events so strange they defy our current imagination. A cosmic Rorschach test where we cannot yet agree on what we are seeing. While the cold spot remains a ghostly imprint on ancient light, a more tangible visitor arrived with its own set of impossible rules. In October 2017, a telescope in Hawaii spotted a faint point of light moving at blistering speed. Its trajectory was not bound to the sun. It was a traveler from interstellar space, the first such object ever confirmed, and it was given a name meaning scout from the distant past, oumuamua. From the moment of its discovery, this visitor defied every expectation. First was its shape. By analyzing how its brightness changed dramatically as it tumbled, astronomers deduced it was not round. It was profoundly elongated, perhaps 10 times longer than it was wide, a shape like a cosmic cigar or a pancake, unlike any asteroid or comet we have seen in our own solar system. Then came its surface. It was dark red, likely baked by eons of cosmic radiation, and it showed no signs of outgassing, the telltale cloud of gas and dust that forms a comet's glowing coma and tail. It appeared utterly inert, a silent, dark rock from another star. But the greatest defiance came as it was leaving. Precise tracking revealed that oumuamua was not moving under gravity's influence alone. As it sped away from the sun, something was giving it an extra, tiny push. This non-gravitational acceleration was subtle but undeniable. For a normal comet, this is easily explained. Sunlight heats icy surfaces, causing jets of gas to erupt, acting like natural rocket thrusters. Yet every attempt to detect this gas or dust around oumuamua came up empty. No plume, no coma, no chemical signature. It was accelerating in perfect silence. The scientific community scrambled. Could it be releasing gas from unusual ices, like solid nitrogen or hydrogen, that leave no visible trace? Perhaps its strange shape meant it was venting gas from a hidden fissure. A cosmic steam whistle pointed away from our telescopes. But each natural explanation felt strained, requiring a composition or behavior unlike anything in our solar system. The profound lack of a visible coma, the very hallmark of cometary activity, made the acceleration seem almost phantom-like. This persistent mystery opened the door to a more speculative, yet scientifically considered idea. What if the acceleration was not from gas, but from light itself? The pressure of sunlight, while incredibly weak, can exert a force. For a human, it is imperceptible. But for an object that is extremely thin and lightweight, it could act as a sail. If oumuamua was less than a millimeter thick, but as wide as a football field, this solar radiation pressure could explain its push without any gas at all. Such a structure could be natural, a fragment of a shattered planet, or a bizarre shard of icy debris shaped by unknown forces. Or, as a few scientists cautiously proposed, it could be something else entirely, an artifact of a technology, a discarded light sail from a distant civilization. This was not a claim of discovery, but a statement of profound ignorance. Oumuamua fit no ready category. It was an asteroid that accelerated like a comet, but without a comet's signature. It was a visitor with a shape never before seen, behaving in a way that left our best models wanting. Its brief passage was a masterclass in cosmic humility. We were presented with a sample from another star system, and it obeyed rules we did not fully understand. A silent scout that passed through our neighborhood, whispered a secret, and vanished back in the dark. Oumuamua's silent acceleration was a puzzle from the stars, but a claimed invention right here on Earth promised to rewrite the rules of spaceflight itself. It was called the EM drive, or electromagnetic drive, and its proposal was deceptively simple. Imagine a sealed, cone-shaped metal chamber. You pump microwaves into it, they bounce around inside, and somehow, without expelling any fuel or propellant whatsoever, the device generates a tiny, persistent push in one direction. This was not science fiction, but a series of laboratory experiments that reported exactly that, a whisper of thrust from nothing. If true, it was a revolution. Every rocket engine ever built works on Sir Isaac Newton's third law. For every action, there is an equal and opposite reaction. You must throw something out the back, whether it's superheated gas or ions, to push yourself forward. The EM drive claimed to break that fundamental law. It suggested you could create thrust from a closed system, like sitting inside a car and pushing on the dashboard to make the whole vehicle move. By the sacred principle of conservation of momentum, this should be utterly impossible. Yet, several independent teams, including a respected group at NASA Eagle Works Laboratory, reported detecting that impossible signal. Their tests, conducted on highly sensitive torsion balances in vacuum chambers, showed a minuscule but consistent thrust, just a few micronewtons, a force so small it's like the weight of a single grain of sand. But in the frictionless void of space, such a tiny push, if sustained by solar power alone, could theoretically accelerate a spacecraft to incredible speeds over time, enabling journeys to Mars in weeks, not months. The scientific community reacted with intense, profound skepticism. Extraordinary claims require extraordinary evidence, and a violation of momentum conservation is about as extraordinary as it gets. Critics swarmed, pointing out possible hidden sources for the thrust. Could it be an experimental artifact? The minuscule force could be caused by the thermal expansion of the device as it heated up, or magnetic interactions with the Earth's field, or even the subtle push of heated air molecules in a vacuum chamber that wasn't perfectly empty. Each new test seemed to fuel the controversy rather than settle it. Proponents refined their devices, critics designed more rigorous experiments, and the tiny signal persisted, dancing at the very edge of detectability. The likely resolution, after years of global scrutiny, is a sobering lesson in measurement. The most careful subsequent experiments, particularly one by a team in Germany that used a sophisticated pendulum in a near-perfect vacuum and accounted for thermal effects with extreme precision, found that the thrust signal vanished when all known sources of error were eliminated. The thrust, it appears, was not a new physics, but a ghost in the machine, a subtle thermal or electromagnetic interaction masquerading as momentum. The EM drive controversy stands not as a story of a failed breakthrough, but as a masterclass in how science confronts the impossible. It shows the thrilling allure of a rule-breaking idea, the rigorous gauntlet of skepticism it must survive, and the ultimate power of meticulous, repeatable experiment. Sometimes, the universe's greatest defiance is not of physical laws, but of our own ability to measure them perfectly, reminding us that the line between a revolution and a measurement error can be vanishingly thin. Tabby's star's initial strangeness was just the opening chapter. While the sharp, chaotic dips captured by Kepler were shocking, astronomers soon uncovered an even more perplexing layer to this mystery by looking backward in time. They scoured over a century of archival photographic plates from observatories like Harvard, which had been meticulously digitized. This historical record revealed a breathtaking trend. The star's overall brightness has been steadily, mysteriously fading for more than 100 years. This was not a sudden event, but a glacial dimming, a slow-motion dimmer switch being turned down across generations. Combine this with the sharp, day-long plunges of 20% or more, and you have a star behaving in two impossible ways at once. A swarm of comets might explain the irregular dips, but could it also cause a century-long decline? A colliding planetary debris field would be a one-time event, not a persistent fade. This dual behavior defied any single, simple explanation from our cosmic playbook. The hunt for answers intensified, with telescopes across the globe and in space training their eyes on this one point of light. The critical breakthrough came from watching how the star dimmed across different colors of light. When an object like a planet or an asteroid passes in front of a star, it blocks all wavelengths equally, like a dark rock in front of a white light. But the subsequent observations of Tabby's star showed something different. The dimming was more pronounced in blue light than in red light. This is a classic fingerprint of dust. Tiny dust particles, smaller than a grain of sand, scatter blue light more effectively than red, just like our own atmosphere makes the sky appear blue. The evidence began to pivot away from solid, opaque megastructures and toward a colossal, uneven cloud of fine cosmic dust. So, case closed, just an ordinary dust cloud. Far from it, this is where the puzzle deepens from a question of what to a question of how. The dust is undoubtedly there, but its origin and bizarre behavior remain profoundly strange. Ordinary interstellar dust drifting between us and the star would not cause the sharp, irregular dips. It would create a smooth, gradual dimming. This dust must be local to the star system, orbiting in a tight, clumpy, and incredibly asymmetric swarm. What natural process could create such a thing? A recent catastrophic collision between planets could eject immense amounts of pulverized rock, but models suggest such a cloud would spread out and dissipate relatively quickly on astronomical timescales, not maintain its clumpy structure for the century we have been watching. Another leading idea points to exocomets, not just a few, but a family of them on wildly eccentric orbits, disintegrating as they swing close to the star and trailing enormous plumes of dust and debris. Yet, the scale required is mind-boggling, demanding thousands of giant comets to explain both the deep dips and the long-term trend. Even the dust itself is puzzling. Its particles must be incredibly fine to scatter blue light so effectively, but such tiny grains are usually blown away by the star's radiation pressure almost immediately. Something must be continuously replenishing this cloud, or holding it in place against the stellar wind. So while the alien megastructure hypothesis has faded like the star itself, what has taken its place is arguably just as compelling. We are left with a star that is, without doubt, shrouded by a colossal and intricate dust cloud of unnatural shape and persistence. The universe has crafted a natural phenomenon so extreme, so dynamically complex, that it perfectly mimicked the signature of artificiality, pushing our understanding of stellar systems to a new and bewildering frontier where even the simplest answer, dust, comes with a universe of questions. That whisper of thermal recoil from the Pioneer probes did more than solve a single mystery. It fundamentally changed how we explore the cosmos. The Pioneer anomaly's true legacy is not a rewritten law of gravity, but a rewritten rulebook for spacecraft design and deep space navigation. For decades, that tiny, unexplained deceleration was a constant thorn in the side of physicists and engineers, a signal that our understanding of the forces acting on a spacecraft, even in the apparent vacuum of space, was incomplete. This persistent defiance forced an unprecedented level of scrutiny. Teams around the world spent years performing forensic archaeology on the probe's decades-old blueprints, reconstructing their exact thermal properties, the paint on their surfaces, the heat radiating from every instrument and electrical component. They had to model not just the sunlight falling on the spacecraft, but the infrared glow radiating from every square inch of its structure, and crucially, how that emitted heat carried a tiny amount of momentum away. This was physics on a breathtakingly minute scale, where a warmth you could barely feel with your hand became a navigational force over interstellar distances. The ultimate resolution, attributing the anomaly to thermal recoil, was a triumph of scientific diligence. It proved that the universe was not breaking its own rules. We had simply failed to account for one of them in sufficient detail. The lesson was profound and permanent. Today, the ghost of the Pioneer anomaly flies on every mission beyond Earth's orbit. Engineers now build exquisitely detailed thermal models for spacecraft like New Horizons and the Voyager probes, accounting for the subtle push from every watt of power dissipated, from the warmth of a computer chip to the decay heat of a plutonium power source. This vigilance allows for navigation with pinpoint accuracy across billions of miles. The anomaly taught us that deep space is not a perfect void. It is an environment where even the faintest whisper of heat becomes a steering force. It shifted our focus from hunting for cosmic phantoms to mastering the intricate dance of real-world engineering. In doing so, it made our spacecraft not just explorers, but precision instruments, capable of testing the fabric of reality itself because we finally learned how to account for the warmth of their own beating hearts. A different kind of ghost haunts the quantum realm, a connection so intimate it seems to erase the very concept of distance. This is quantum entanglement, a phenomenon so bizarre it prompted Albert Einstein himself to dismiss it as spooky action at a distance. He was deeply troubled by its implications, for it appeared to defy the foundational logic of the classical universe he helped build. The principle is deceptively simple. Two particles, like photons or electrons, can be created or interact in such a way that their properties become deeply linked or entangled. They form a single, unified quantum system, no matter how far apart they are later separated. Measure the spin or polarization of one particle, and you instantly know the state of its partner, even if that partner is on the other side of the galaxy. The spookiness lies in that word, instantly. In our everyday world, information cannot travel faster than light. If you separate two coins, flip one, and see it land heads, you know the other is tails because that was its state when they parted. But in the quantum world, The particles do not have definite, individual states until they are measured. They exist in a blur of all possibilities. The act of measuring one does not just reveal a pre-existing condition, it seemingly forces the other, distant particle to snap into a corresponding state at that exact moment. This challenges our deepest intuitions about reality, locality, and information. It feels as if a message has been sent faster than light, violating cosmic speed limits. Yet, meticulously crafted experiments over decades have confirmed this spooky action is undeniably real. Scientists have entangled particles and separated them by hundreds of miles, even sending one to a satellite in orbit. Every time, the measurements show a correlation that is stronger than any classical, local mechanism could explain. The particles remain in a ghostly communion, their fates intertwined across the void. This does not break the laws of physics. It defines the deepest laws of the quantum world. It tells us that at a fundamental level, the universe is not a collection of separate, independent objects. It is a woven tapestry where connections can exist that transcend space, where what happens here is intimately linked to what happens there, not through a signal we can intercept, but through a shared existence that operates on rules far stranger than any fiction. The ghostly connections of quantum entanglement reveal a universe woven together at its core, but another cosmic phenomenon tears that fabric apart with raw, obliterating power. Gamma-ray bursts are the universe's most violent explosions, sudden blasts of high-energy radiation so intense they can outshine every star in every galaxy combined for a few fleeting seconds. For decades, they were the ultimate cosmic defiance, appearing without warning from random points in the sky, blazing for mere moments, and then vanishing into darkness, leaving behind only a fading afterglow and a profound question. What natural engine could possibly concentrate more energy than our Sun will emit in its entire 10 billion year lifetime into a focused beam that lasts less than a minute? The answer was locked away by their very nature, too fast and too unpredictable to catch in the act. Solving this mystery required a revolution in how we watch the sky. It began with dedicated satellites like NASA Compton Gamma Ray Observatory and later, the Swift and Fermi missions, designed not just to see the initial flash, but to swivel with lightning speed, autonomously pointing other telescopes at the burst's location within seconds. This rapid response was the key. It allowed astronomers to capture the afterglow, the fading echo of the explosion across X-ray, optical, and radio wavelengths, and crucially, to pinpoint its home galaxy. The data revealed a critical clue. Gamma-ray bursts came in two distinct flavors: long bursts lasting more than 2 seconds, and short bursts lasting less than 2 seconds. This simple division pointed to two completely different cosmic catastrophes. The long bursts held the first breakthrough. In their fading afterglows, astronomers began to detect the unmistakable fingerprint of a supernova, the titanic explosion of a massive star. But this was no ordinary star death. This was a hypernova, the collapse of a star dozens of times more massive than our Sun, its core collapsing directly into a black hole. As the star's outer layers plummet inward, they form a swirling disk of superheated material around the newborn black hole. Powerful magnetic fields and neutrinos channel some of this infalling matter into two ultra-relativistic jets, piercing through the star's carcass at nearly the speed of light. If one of those jets is pointed directly at Earth, we see it as a long gamma-ray burst, a stellar death scream focused into a cosmic blowtorch. The short bursts, however, guarded their secret more closely. Their brevity suggested an even more compact, faster cataclysm. The leading theory was a merger, the final, fatal dance of two super-dense stellar corpses, either two neutron stars or a neutron star and a black hole. As these objects spiral together over millennia, they rip spacetime itself, emitting ripples of gravitational waves. In their last milliseconds, they collide, spraying out a blizzard of neutron-rich material that forges heavy elements like gold and platinum in a rapid nuclear forge, and again powers a pair of ultra-fast jets. For years, this was a beautiful theory without its smoking gun. Then, on August 17, 2017, the universe provided the proof. The LIGO and Virgo gravitational wave observatories felt the distinctive chirp of two neutron stars merging, a ripple in spacetime. At almost the same instant, just 2 seconds later, the Fermi satellite saw a short gamma ray burst from the same patch of sky. This was the dawn of multi-messenger astronomy, observing the same event through different cosmic senses, light and spacetime waves. The follow-up observations were a scientific bonanza, capturing the kilonova, the glowing radioactive debris from the merger, and confirming it was indeed producing mountains of heavy elements. In one breathtaking moment, a short gamma-ray burst was transformed from a defiant mystery into a cornerstone of astrophysics. It linked the birth of black holes, the creation of the universe's heaviest elements, and the propagation of gravitational waves into a single, coherent story. The defiance was not a broken law, but a hidden connection, waiting for our technology and patience to reveal how the universe's most destructive acts are also its most creative. That violent creativity of gamma-ray bursts unfolds across the cosmos, but a far more intimate and persistent defiance burns right in our own sky. The sun's visible surface, the photosphere, glows at a familiar 6,500 degrees Kelvin. Yet, just a few thousand kilometers above it, in the wispy, ethereal outer atmosphere called the corona, the temperature soars to over 1 million degrees. This is not a gradual climb. It is a dramatic, violent temperature inversion, like walking away from a campfire and suddenly stepping into a blast furnace. It defies the most basic rule of thermodynamics, which says heat flows from hotter regions to colder ones. If you hold your hand above a light bulb, you feel warmth rising from it. The sun inverts this logic entirely. Its core is unimaginably hot at 15 million degrees, but that heat slowly radiates outward, cooling as it goes, until it reaches the visible surface. Then, mysteriously, the temperature spikes again in the thin plasma of the corona. For over half a century, this coronal heating problem has been one of the most stubborn puzzles in solar physics. How does the sun pump so much energy into its tenuous outer atmosphere? The answer is woven into the star's magnetic soul. The sun is not a solid ball of fire, but a churning, dynamic sphere of superheated plasma, a gas so hot its atoms are stripped of their electrons. This plasma is threaded with immensely powerful and constantly tangled magnetic fields, generated by the motion of the plasma itself. These magnetic fields are the engine of the corona's heat. One leading theory points to constant tiny explosions. The sun's magnetic field lines are like elastic bands, constantly being twisted and braided by the turbulent motions below. When these lines become too stressed, they can snap and reconnect, releasing energy in miniature bursts called nanoflares. Each one is minuscule compared to a full solar flare, but theorists suggest they could be so numerous and frequent that together they provide the steady heat needed to cook the corona. Imagine trying to heat a room not with a single bonfire, but with billions of microscopic firecrackers popping every second. The challenge is that these nanoflares are too small and faint for our telescopes to see directly against the sun's overwhelming glare, so their existence remains inferred from the corona's intense energy. Another compelling idea focuses on waves. The sun's convective churning, the bubbling motion that gives the photosphere its granular appearance, sends powerful vibrations rippling through the solar interior. These vibrations can travel up into the magnetic field lines that arc through the corona, transforming into magnetohydrodynamic waves. As these waves travel upward into the thinner plasma of the corona, their energy can dissipate, dumping heat into the surrounding gas. Think of it like an ocean wave that grows taller and more turbulent as it approaches the shore, finally crashing and releasing all its pent-up energy. Observing and quantifying this wave heating is a monumental task, requiring instruments that can track subtle motions and temperature changes in the corona with split-second precision. The quest to solve this mystery is not academic. The superheated corona is the source of the solar wind, the stream of charged particles that flows outward, shaping the space environment of our entire solar system. It drives solar storms that can disrupt satellites and power grids on Earth. Understanding how the corona is heated is key to predicting our star's behavior. Missions like NASA Parker Solar Probe, which flies through the corona itself, and the Solar Orbiter, which provides unprecedented close-up imagery, are now gathering the crucial data. They are measuring magnetic fields, catching particles, and watching for the signatures of those elusive nanoflares and waves. Each new finding brings us closer to reconciling this glaring temperature inversion with the laws of physics, revealing a star that is not a simple ball of gas, but a complex magnetic dynamo, turning the orderly flow of heat into a spectacular million-degree mystery. The sun's corona blazes with unanswered questions, but the ultimate defiance lies not in how a star burns, but in how the entire cosmos will one day fade to black. After journeying through 29 instances where space seems to bend or break the rules, we arrive at the 30th and most profound mystery of all, the universe's own final fate. This is not a puzzle about a distant star or a strange particle. It is the question of how everything ends, and the startling truth is that the laws of physics, as we currently understand them, offer multiple, contradictory endings. The script is not yet written, and the director is a force we barely comprehend: dark energy. The ultimate law of the cosmos, its final act, actively defies our prediction. The leading theory, born from our observation of accelerating expansion, is a finale of profound silence known as the Big Freeze, or heat death. In this scenario, dark energy remains constant or changes very slowly. The expansion continues forever, accelerating galaxies away from each other until every island universe vanishes over the cosmic horizon. Star formation will cease as gas is exhausted. Existing stars will burn out, and black holes will slowly evaporate via Hawking radiation over trillions upon trillions of years. The universe will approach absolute zero, a state of maximum entropy where no energy is available to do work, no light shines, and no complex structures can form. It becomes a vast, dark, and near-empty void where even time may lose its meaning. This is a fate of eternal, frozen stillness, but dark energy might not be so gentle. What if it strengthens over time? This leads to a far more violent and dramatic end, the Big Rip. In this scenario, the repulsive force of dark energy grows without bound, eventually overcoming every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration becomes catastrophic, the gravitational grip holding stars within galaxies would fail. Solar systems would be shredded. In the final, horrifying moments, the force would exceed the electromagnetic bonds holding atoms together, then the nuclear forces within atomic nuclei. Planets, rocks, and finally every molecule, atom, and fundamental particle would be violently ripped apart in a flash of ultimate disintegration. The universe would end not with a whimper, but with a catastrophic tear in the very fabric of reality. Yet, there are alternatives that defy the notion of an end altogether. Some cosmological models, often inspired by certain interpretations of string theory or cyclic cosmology, propose a universe without a true death, a cosmic phoenix. This is the idea of a big bounce or a cyclical universe. In these models, our expanding universe is just one phase in an endless cycle. Eventually, the expansion could slow, reverse, and lead to a big crunch, where all matter and energy collapse back into an ultra-hot, dense state. But instead of a singular endpoint, this state becomes the seed for a new Big Bang, birthing a new universe with potentially different physical constants. Our entire cosmic history, from the first flash to the last black hole, might just be one turn of an eternal wheel. Another variation suggests a multiverse where new bubble universes are constantly budding off from an eternally inflating background, making death for the whole cosmos irrelevant. The fact that we can seriously entertain these wildly different endings, from frozen silence to violent shredding to eternal rebirth, is the core of the defiance. It stems from our fundamental ignorance about dark energy. Is it truly a constant, Einstein's cosmological constant, or is it a dynamic field that evolves? Our measurements are not yet precise enough to say. This means the ultimate rule, the final law that governs the destiny of all existence, remains unknown. The universe holds the answer to its own greatest question just out of reach. Every galaxy racing away, every new measurement of the Hubble tension, is a clue in this grandest of all mysteries. So while we have mapped the universe's birth and traced its epic history, its final chapter is a blank page. The cosmos, in its final act, refuses to reveal the ending, ensuring that the greatest story ever told remains, for now, thrillingly unfinished. From the faint whisper of slowing spacecraft to the silent scream of a dying universe, we have crossed a frontier of cosmic mysteries. 30 astonishing moments where reality seemed to bend its own rules, from the hexagon on Saturn to the phantom pull of Planet 9, from the spooky link of entangled particles to the impossible heat of the sun's crown. Each one, at first glance, appears to be a defiance, a crack in the cosmic code. But look closer. These are not failures of science, they are its very lifeblood. Every anomaly, every paradox, every stubborn piece of data that refuses to fit is a signpost pointing toward a deeper truth. The pioneer anomaly taught us to account for the warmth of a spacecraft's own heart. The hunt for dark matter revealed the hidden skeleton of the cosmos. The frustration of the Hubble tension may be forcing us to rewrite the recipe of the universe itself. These are not walls, they are doors. Each mystery represents a frontier of human ignorance, and therefore a frontier of human curiosity. They remind us that our understanding is a map, and the universe is the territory, always vaster, always stranger. So the next time you look up at the night sky, remember this. You are not looking at a clockwork mechanism bound by simple rules. You are gazing into a living story, an epic still being written, filled with ghosts and giants, with whispers from the dawn of time and visions of an end we cannot yet foresee. Let that fill you not with confusion, but with wonder. Stay curious. Which of these cosmic defiances left you the most baffled, the most awestruck? Share your thoughts below, and if you crave more journeys to the edge of understanding, subscribe and join us as we continue to explore the deepest mysteries of the cosmos. The universe is waiting, and its greatest secrets are still